Our next speaker earned his bachelor's degree in chemistry from Bates College and his master's degree with a focus on the Semiconductor Device Processing from the University of Oregon. He performed graduate research and development at SolarWorld before taking on his current position as a scientist at Polaris Battery Labs, a lithium-ion battery prototyping facility located in Beaverton. He is part of a small team which designs, fabricates, and tests custom lithium-ion cells for large-scale manufacturers, startups, universities, and national laboratories. Much of his work is centered around formulation development and fundamental performance improvement for next-generation electrode materials. Here to discuss the strategies and roadblocks to commercialization of high-capacity lithium-ion batteries, please welcome Nicholas Gurnon.
So at Polaris, we're a small lab. We basically hand build artisanal batteries. They're handmade, they're one of a kind, they're highly customizable. We can build batches of up to, say, 10, 20 cells, but sometimes they're just one-offs. And we start with raw materials like these powders here. This is some of the anode and cathode active materials, some of the binders that hold all the active materials together. We coat those on conductive substrates called current collectors. They're copper foil, aluminum foil. There's a separator that goes in between the two electrodes to keep them from short-circuiting and allow lithium ions to pass back and forth. There's electrolyte inside. There's no picture of that because it's air and moisture unstable, and so it's hard to get a picture of that. Also, it just looks like clear liquid. And then these are some of the cell formats that we can make. So this is a kind of a tiny little guy about the size of a quarter. This is sort of a cell phone size battery. And then this prototype was designed for an e-bike. This is our team. This guy, it looks like this is like an in memoriam photo, but he just wasn't there for the photo. He's still with us. If you can spot the OIP grad, we've actually got 4 in the lab. So this is our small team. So to get a little background on lithium-ion battery function, you have the anode over here at low potential, cathode at relatively high potential. The cathode starts out containing all the lithium. Anode is empty from the very beginning. There's a separator, as I said, in between, so that the electrons travel outside, go through your circuit, rather than directly back and forth. That causes fire and explosions sometimes if you short circuit. But the lithium ions, this is showing discharge. So lithium ions moving from the anode back to the cathode, where they get incorporated into this crystal matrix rather than forming lithium metal. So this is the main distinction between a lithium ion cell and a primary cell or a lithium metal battery, like a coin cell. There should be no lithium metal in a properly functioning lithium-ion battery. You get lithium ions, you get lithium atoms, but no bulk lithium metal. Samsung Galaxy 7s did get some lithium metal, and that was kind of catastrophic. So they short-circuited. Lithium is quite reactive. So it works by stripping a lithium atom of its electron, passing the electron through the circuit. The lithium diffuses from one electrode to the other, reunites with its electron, and you can do that reversibly on charge and discharge. Pretty great. The full potential is about 4.3 volts between the cathode and the anode, so it's very high energy density. Lithium metal has about 3,862 milliamp hours per gram of capacity. Down here is the equation for milliamp and milliamp hour. We don't really need to go into that, but suffice to say, you can calculate how many lithium atoms are changing places and convert that into capacity in milliamp hours. Very high potential for lithium metal, but also a lot of safety risks. It also isn't rechargeable. There's losses every time you try to use it. So the actual cathode material ends up being about 175 milliamp hours per gram. And this is graphite. So graphite is about 370. It is the most widely used anode material. And I'm going to have to speed it up. So in a typical phone, you've got about 1960 milliamp hours and 2900 for a big iPhone S. This equates to about half a gram of lithium or 3/4 of a gram of lithium. So the solid electrolyte interface is the reason that we can't use a lot of very high capacity materials in the anode, and I'll get into more of that later. Solid electrolyte interface is, as it says here, complex, heterogeneous, difficult to study, and it's basically magical. It forms a passivating layer on the anode surface. The electrolyte is simply not stable over the voltage range of 0 to 4.3, and it undergoes reductive decomposition at the anode at the low voltage. So, on the first charge with graphite, you develop this SEI layer through decomposition of the electrolyte, but it's a self-passivating film. It's like aluminum oxide on aluminum. It prevents, in a well-functioning battery, it prevents further solvent reduction. And that's important because as you consume solvent, which contains the electrolyte here, lithium and hexafluorophosphate, you decrease the conductivity of the electrolyte. So you increase the resistance of the cell. You also remove lithium. So lithium is contained in the SEI layer. Lithium is what gives you the capacity. So you lose capacity, you increase resistance. So if your SEI layer isn't formed correctly, and if it doesn't stay just perfectly stable, you lose capacity. The electrolyte itself has to be a very special solvent, a very special mixture, in order to form a good SEI layer. Can't be water, because water reacts violently with lithium, and it also forms a caustic mess if you put the two together. So these are typical solvents. This is through chance, luck, experimentation. We found that these cyclic carbonates and linear carbonates decompose to form a really nice, robust SEI layer. Mostly this one, ethylene carbonate. But it's not liquid at room temperature, so you have to dissolve it in other solvents. Now, not all anode materials are created equal, so the graphite, 370 milliamp hours per gram, sounds pretty good. But silicon has more than 10 times that capacity. So why don't we use it? Why isn't it everywhere? You can get 22 lithium ions, or lithium atoms, for every 5 silicons. In graphite, it's 1 lithium for every 6 carbons. So the stoichiometry is way, way, way better for silicon. This is an illustration of the energy density of silicon versus graphite. But graphite is everywhere. So why don't we use silicon? Well, all that lithium has to go somewhere. You can't just put something into something else and not expect it to get bigger. So lithiated graphite, LiC6, has about a 10% volume expansion. Not a lot. Lithiated silicon, oh sorry, this is a little messed up, but has a 300% volume expansion. So you're expecting that SEI layer to hold up as you expand to 3 times its original size. And then on contraction, when you delithiate, you discharge the anode, you contract back to the original size. So that SEI layer has to be like rubbery, very, very forgiving of these things. So what really happens, with silicon you get volume expansion of the particles, they contract, and over many cycles they get pulverized. Now you've got these small particles that become in electrical isolation. Everything has to be electrically connected to that foil, the current collector. Silicon itself is not very conductive, it's a semiconductor. And so if you lose good electrical connection to that current collector foil, you lose capacity also, because it's just floating around in the electrolyte doing nothing. The other thing that happens, and I just mentioned this, was that the SEI layer has to balloon up, and then as the silicon shrinks down, the SEI layer breaks, that floats away, and then on the next cycle, you've got to form more SEI layer and consume more lithium. So you lose capacity every cycle. Whereas graphite's really well behaved, and 10% up, 10% down, you get like thousands of cycles out of cells with graphite anodes. This is kind of hard to see, but this is an illustration of pristine silicon and then cycled silicon. It's all gunky, everything's kind of, it's a thick SEI layer, particles are all kind of crunched together, high impedance and capacity loss. So this is I just think this is really pretty graphic, but there's a lot here. So the main idea is that you lose capacity with cycling on silicon, your voltage goes up, which means that you start pushing the cathode into unsafe voltages, and then you get a very unsafe situation, and lot of capacity loss. So one of the strategies that people are using, and these are all strategies that our clients have used. I can't talk specifically about their projects, but these are kind of general approaches. Use smaller particles. There's less differential expansion stress. You have to diffuse it from the outside. So if you have a smaller distance between the core that's unlithiated and the outside particle that is fully lithiated, you get less differential stress overall. So if you've got particles that are, say, 50 nanometers, very, very tiny, this is a representation of 50 nanometers. So strange unit, but 20 square meters per gram of silicon at 50 nanometers. So if you took 50 nanometer, like a spoonful of 50 nanometer silicon, that is 20 square meters of surface area. Now remember, you have to form SEI on all of the surface that's exposed to the electrolyte. This is a typical graphite particle, 20 micron diameter. There's 10 times less surface area in the graphite. And since all the surface has to be covered with SEI, 10 times more SEI per gram of material in the silicon. So 10 times more lithium loss on SEI formation. Okay, well, what happens if you start monkeying with the electrolyte to make it better able to withstand that expansion and contraction, or make it so that it forms a thinner layer, consuming less lithium? If you go from ethylene carbonate and just put a fluorine on there, now it's fluoroethylene carbonate, FEC. This has done tremendous things for allowing for the commercialization of silicon anodes. This is cycling capacity with FEC, and this is cycling capacity without FEC. Now this is misleading because this is a research paper, and that's what people do. They present their best data. This is a very, very thin electrode that doesn't have enough energy density for a commercial cell, but it illustrates the importance of working with the electrolyte. This is great. So this is a plot of the first lithiation. This is where the bulk of the SEI formation happens. With FEC, you get a little bit of a current bump at starting at about 1 volt. With EC, that really starts at about 0.8 volts. So what this tells you is that this preferentially decomposes over the ethylene carbonate. It decomposes at a higher voltage, and it actually ends up forming a more robust, more elastic SEI layer. Oh, erase this again. So again, this is pristine electrodes. This is 30 micron scale bar. This is 200 nanometers, so really zoomed in. Silicon particles, about 50 nanometers. This is electrolyte without FEC, and this is, these are without FEC. You see cracking, you see agglomeration, you see kind of gunk. After cycling with FEC, still a nice pristine surface and individual particles still there. That's not the full solution though, because FEC has problems at different temperatures. It does fade in bulk electrodes. In very thin films, it actually does a remarkable job. So what if we limited the expansion and contraction of the silicon particles by limiting the voltage range that we use, the state of charge? So if we didn't fully lithiate, we wouldn't go all the way to 300% expansion. If we didn't fully delithiate, we wouldn't go all the way back to the starting point. And so you put less stress on the SEI layer that way. Well, strategy 1 here is, okay, so we only lithiate to 1,200 milliamp hours per gram. It's still about 3 times more capacity than graphite per gram. So you only get about 100% volume expansion. But your voltage is at 150 millivolts. Cell voltage is the cathode minus the anode. So if the anode voltage is relatively high, you have a low overall cell voltage. If you fully lithiate, you get almost all the way down to 0 volts. And so you maintain that full cell voltage. In both cases, we're operating at about 1,200 milliamp hours per gram. In this case, the overall cell voltage is lowered, so you reduce the volumetric energy density of the cell. In this case, if we fully lithiate and then only partially delithiate, we're operating in a relatively low voltage range, so you get all the cell voltage, but you still have to form all of this SEI. And so you lose a lot of capacity irreversibly on the first cycle, and you just never get it back. So both of these strategies are definitely tools, but they're not. None of these are panacea. And so this is what happens if you limit the charge and discharge to 1200 milliamp hours. This is the lower discharge voltage. In this case, they fully charged it, and then they're only partially discharging. So you can see the lower voltage, it's having to go to deeper and deeper and deeper discharges to get this capacity as you cycle. And that's because here's the difference between the lithiation and delithiation capacities. All of this, the distance between these two lines is all capacity loss on forming new SEI layer. So the final thing, which is really cool, is people are very creative. I mean, we work with all these other technologies, and all these things have to happen kind of in concert. A lot of these strategies are used together. This is my favorite. I love when we get to work with engineered morphologies. Nanowires, and not just silicon. I mean, I've talked mostly about silicon, but there's other materials. Nickel, tin, nickel silicide. Lots of these materials have much more higher capacity than graphite, but they all suffer from these same issues due to expansion, contraction, SEI formation, and lithium consumption, and also the anode voltage versus the voltage of graphite. So nanowires, you get essentially one-dimensional transport of electrons through the nanowires. You get not a lot of strain because there's only really one-dimensional expansion and contraction too. These are actually commercialized by Amprius. Since they're using a truncated voltage range and they are using different electrolyte additives that are not necessarily helping the capacity, you still only get about a 20 to 25% boost in overall cell energy density by using this type of situation. They've got about a 625 watt-hour per liter cell that's about to be commercialized or already is. And that's, I mean, that's great, 20 to 25% improvement. But for a material that has a theoretical capacity more than 10 times higher than graphite, all that stuff gets diluted out. Yes?
So are those nanowires, are those on the surface of the anode, or are they the entire anode themselves?
They are on the surface. Yeah, that's a good point. And so I need to make that distinction because all these other processes I've talked about are basically like slurry coat. You basically paint the electrode material on the foil. It's a very cheap process. These nanowires have to be grown on the foil under vacuum in a vapor deposition process. Very expensive, and I mean, Amprius has figured out how to do it in high throughput, but the throughput between, the difference between like putting something in a vacuum chamber, growing nanowires, and then just slapping the slurry on the foil, there's more to it than that, but that's what we do at Polaris. We just paint the foil, basically. So there's a lot more processing that goes on here, but this actually works. This is probably my favorite. This is the encapsulated silicon. People make a conductive, like candy shell, and they've engineered a nano particle that has a little bit of silicon on the inside, and so this conductive shell allows it to maintain electrical conductivity to the rest of the anode and to the current collector, and it allows the lithiated silicon to expand within that shell without cracking, and so you maintain electrical conductivity. This is a very expensive way to go about business. It's really impressive from a material science and engineering point of view, but it's a little bit a ways from commercialization. I also like it because of the comparisons to food that you'll see in papers. Egg yolk, yolk shell is a typical. I've also seen avocado and pomegranate for these things. And then I'm actually doing a lot of work with people who are doing this type of thing, and they'll surface treat the silicon, either coat it with graphene or another conductive carbon substance, so that you can then slurry coat it. You can paint it on, but then you've got to do this in combination with all those other tricks that we talked about earlier. And the carbon coating decreases that volumetric energy density, because now you're not operating with just silicon. Now you've got carbon, which is lower capacity. But this is promising also because at least it allows for cheap and easy processing. So I think that's those. And then, so I think that's it. Anybody have questions? Sorry I had to run through that. I get very excited about batteries. So if you would like to talk more about batteries or about components in addition to the anode, please get in touch with me. But anybody questions for now?
Yeah. So, what is the best way to make my laptop battery last a long time?
Well, there's a battery management system in it. So it should take care of things, but if you don't fully discharge and you don't keep charging it when it's already at like 90% charge, that'll help. So if you operate in the window of like 20% to 80% capacity, so if you don't let it go all the way down to die, that helps. It's just you're basically putting less stress on the components, and you get less. The electrochemical processes of electrolyte decomposition are going on all the time. I mean, with time and especially with heat, also don't let it get too hot, because these things, heat dramatically speeds up chemical reactions. And so this reaction that consumes lithium is basically happening anytime the anode is below about 1 volt, which is for most of the state of charge of your battery.
So you were going to tell us about some of the projects that your customers are involved with, but can you point us in the areas of technology that these new innovations are going to land?
Oh, you mean the applications? Yeah. So the question was on where are some of these new innovations in the morphology and the additives and in the processing of the silicon? Where are they going to end up in terms of application? Well, the nanowires, that is a great one because you get really good rate capability. You can get very fast diffusion into and out of the silicon because it's got a high surface area, very, very thin particles, or very thin nanorods. So that could be automotive, that could be consumer electronics that are especially like power tools where there's a high pulse power demand. And graphite just can't keep up, especially in terms of charging. You can lithiate those nanowires very quickly. So fast charge consumer electronics, fast charge cars even. But a lot of the other ones are going to be better for long-term energy storage. You can do grid storage applications because if you have a giant truck in the middle of the desert with your batteries, who cares if it's a little bit bigger than it needs to be? But the kind of the bulk coating processes where you've got the graphene encapsulated silicon, those you can coat much thicker and get higher energy density, but the rate capability is not great. So for low power devices or for as a long-term storage, those are going to be better because you can operate them at a slightly higher voltage. You can slow down this decomposition, but you're not going to get very good rate. So all the morphologies and the approaches have trade-offs between basically energy and power. So they're all over the place. Graphite is amazing that it's gotten us this far, but it's being phased out, essentially. Did you have a question?
Yes. I don't know if I understood this correctly, but you mentioned that lithium ion, the electrons flow from the anode to that lower potential to the cathode, which is at a higher potential. It's not exactly how this works.
The electron prefers to be at a higher voltage because it is a more positive voltage because it is negatively charged. And so as a chemist, just trying to get into electrochemistry, it took me a while to wrap my head around this because you would think, well, why doesn't the electron want to go to low potential? But it is actually, from the electron's point of view, it's the opposite. It's under a lot of stress here, it's at a high energy, and so it really wants to get back over here and find a cozy home in the crystal lattice, where it's at because electrochemistry is all about, and chemistry in general, is all about the environment that you're in and what the electron feels, how it, the energy and the potential for it, sorry to use potential in that way, but the potential for it to leave and find a home with a different molecule where it's at a lower energy, higher potential. So it's kind of counterintuitive. But here, yes, the electrons are in a higher energy state than they are here. And so if you connect the two, they will spontaneously come back. The reverse process, you have to put energy in, which is why you plug your phone into charge. Thank you, guys.